In this interesting problem, we're going to look at how to use vector methods to prove a classical theorem of geometry. It's a theorem called Varignon's theorem. Varignon was a French mathematician who lived in the 17th century. He discovered the following interesting fact: that if A, B, C, D is a convex quadrilateral, and you look at the midpoints of the four sides, then the quadrilateral formed by those four midpoints is in fact a parallelogram, which means that the opposite sides are both parallel and have the same lengths. So we're going to prove that using a little bit of vector geometry. So to start off with, let's introduce some notation. I've drawn a diagram. I'm now going to officially introduce the points that I've labeled on the diagram. So I'm going to say, let L, M, N, and K be the respective midpoints of AB, BC, CD, and DE. Of AB, BC, CD, and DA. So that means that L is the midpoint of AB, which we could denote by the usual kind of symbol like that if we wanted to. M is the midpoint of BC, so these two are the same. N is the midpoint of CD, so these ones are equal. And K is the midpoint of DA, maybe like that. Okay, and I'm also going to introduce some vectors into the story. The four sides of the original quadrilateral form four vectors. So let's give them some names. Let's define the vector A to be the vector AB. Put a hat on that. All right, so that's the vector from here to here. In the diagram, I would put an arrow there, and then that would be the vector little a. The vector B is the one from B to C, so from here to here, that would be the vector B. Vector C is from C to D. There it is there. And the vector D from D to A. All right, so we've introduced the four vectors. All right, now let's try to express the sides of this interior quadrilateral in terms of these four vectors A, B, C, and D. But before we do that, let's note that there's a relationship formed by these four vectors. So we're going to note that if we add up the vectors A plus B plus C plus D, we're going to go all the way around this quadrilateral and back to where we started so that the total vector is the zero vector. So this is a linear relationship formed by these four vectors. They are not independent. All right, so now let's have a look at the sides of this interior quadrilateral. So now let's have a look at the vector from L to M, LM. Let's try to express that in terms of the vectors A, B, C, and D. So LM is the same as LB plus BM. And what is the vector LB? Well, it's obviously related to the vector A. From here to here is the vector A. This is the midpoint of the side AB. So the vector from L to B is exactly half of A. So this is 1/2 of the vector A. And similarly, the vector BM from here to here is 1/2 the vector from B to C, which we're calling vector B. So BM is the vector 1/2 of B, comma. And let's look at the corresponding side KN. Because we're trying to show that this is a parallelogram, which means that we're trying to show that this side is parallel and equal to this side. In other words, that this as a vector is actually equal to this as a vector. That's the essence of being a parallelogram. So we've got control of LM. Let's get control of KN. All right, how do we go from K to N? Well, we can get from K to N by first going to D, so KD, and then from D to N. All right, what can we say about KD? Well, KD from here to here is related to the vector D, but D goes from here to here. So this is halfway along, but also in the opposite direction. So it's minus 1/2 of D. That's what KD is. And similarly, DN is halfway of the vector C, but in the opposite direction. So this is plus minus 1/2 of C. So we can write that as minus 1/2 of D plus C. All right, so now we can ask, why is it that LM equals Kn? How can we see that 1/2 of A plus 1/2 of B is equal to the same as minus 1/2 C plus D? Well, it's because of this relation here. All right. So since A plus B plus C plus D equals 0, it follows that it follows that 1/2 of A plus B plus 1/2 of C plus D equals 0. And so 1/2 of A plus B equals minus 1/2 of C plus D. i.e., we've just shown that LM equals Kn. And if two opposite sides of a quadrilateral are equal as vectors, then it's a parallelogram. So LMNK is a parallelogram. And that's the end of our proof of Varignon's theorem, going back to the 1600s.